it a force?
There is a magnetic force. Again, magnetism, we're talking big category. Force is just one aspect of it.
Right.
Yeah. Yes. All right, what do you know about magnets?
They pull metal.
Not all metal, but
They attract something.
yes.
They have a field.
Okay.
They repel each other. They're the same side.
They repel each other, but they're made of metal, aren't they?
Yes.
Why would they not attract?
Because they have negative charge. If they're polarized, right?
How? How do we label the polarization?
Is it north and south?
It is indeed north and south. It is not plus and minus. Unless magnetic monopoles exist. All right, so magnets have a north and south pole. And contrary to recent publicity, if you put a magnet in water, it is not destroyed. What happens if you break a magnet in half?
Doesn't the magnet polarizes the two parts? Does it?
Yeah, I think we got the essence of it. We basically create two smaller magnets. Now, the magnetic field that was also mentioned comes the field lines, and we can potentially stun with visual effects here. The field lines come out the north and into the south. Externally, internally, it's traveling south to north.
So, on the outside, the field lines are they going in a circle, or are they just going like back and forth?
They go in, well, not exactly a circle, but they do go in a loop.
And so, on the outside, they go clockwise, and on the inside, counterclockwise?
I think north to south is the simpler way of saying it. You say clockwise or counterclockwise, it depends on where you orient the magnet.
Okay, so it just starts from the bottom and goes towards the top and then back around.
Internally, it goes from south to north. Externally, it loops back around.
So it'll go from south to north all the way back to south.
Yes.
External.
Yes. Now, typically, you'll see magnetic field lines go from north to south. There's an understood externally. Now, the reason I wanted you to get rid of the idea of plus and minus is that I've had students in the past think about it in terms of plus and minus, and they get really confused because you got positive and negative charges, positive and negative magnetic units, whatever they would be called. There was too much mixing of the concepts. Now, if I take a magnet and I break it up into north and south, and I break it up again, I still have a north and south, and each one as I break it up, in practicality is weaker than the previous one. I will never be able to officially break it down until I just have a south, or just have a north, because the field lines are running around like that, so if I break it in half, I still have field lines coming out this way, coming out that way. And so I still have a north side and a south side. A side note, well, back up. This is not a side note. These are known as magnetic dipoles. An electric dipole, I can't talk and write at the same time apparently. All right, so these are magnetic dipoles. If I have an electric dipole, that means I've got a positive and a negative charge. So electric dipole. I have a positive and a negative charge separated by some distance. And there's this thing called a dipole, electric dipole moment. Q. This is electric dipole moment. And there is a magnetic parallel to that called the magnetic dipole moment.
What is it, the S?
S is the distance between the charges.
And then is that displacement as the vector?
That P right there is the symbol used for electric dipole moment. It
Well,
looks
I'm
a whole-
saying the S in the formula is a vector, so is that displacement or?
It is a vector that goes from the negative to the positive. Yeah, it is a displacement of sorts, but it's a little bit more set of, things don't have to move for it to exist, other than it is a vector going from the negative to the positive direction.
What's the distance between the two poles?
And the magnitude is the distance between the two poles. Now there is a magnetic dipole moment whose symbol is, wish they hadn't done this, but they did. Magnetism starts with an M. What Greek letter starts with an M? Mu. Hey. So we have mu here, which is the magnetic dipole moment. It is a vector. Not to be confused with mu, which is the permittivity, not permittivity, the, why am I suddenly blanking?
Or friction?
No, that too. Permeability, wow. There's also a mu, which is the permeability, which is the magnetic analog of permittivity. There's also the mu, which is the coefficient, or the prefix, meaning 10 to the negative 6th. And that's probably good enough for now. There is a video I did, do not confuse these mu's, where I talk about all the different mu's that show up in physics. Unfortunately, 3 of them show up in magnetism.
Wasn't there something in 151 too that used mu, other than friction?
Oh, linear. Sometimes linear density, I use mu for linear density.
So would you say that you could use this mu with the vector sign, and that's how you know the difference?
Yeah, but if you're talking about the magnitude of it, the magnitude, I put lines around it like that, or I could just write mu.
Okay.
No, ideally I'll do it this way, not so it doesn't get confused with the others, but yeah, the dipole moment has a vector. We'll get to that in more detail later. All right, so because charges can exist as a monopole, in other words, I can have just a positive charge or I can have just a negative charge. I can't do that with magnetism, maybe. As far as this course is concerned, it's a dipole, it will always be a dipole. There are some physicists who are trying to find the magnetic monopole, which surely would be a Nobel Prize. But a magnetic monopole still has a north and south end, or north and south pole. But a magnetic monopole is you'd have a south pole that looks like it's all by itself, and then through some sort of quantum connection is connected to a north pole somewhere else. But we would only see this. There is a theoretical basis for it. It has not been found. There are some physicists who spend their career trying to find it. I heard, I don't know if it's a true story or not, but I'm going to share it anyway. There was a story that there were some grad students who decided to play a practical joke on their professor, and they faked the data, so it looked like they found a magnetic monopole. As a graduate student, I found this very funny. Now that I'm not a grad student anymore, it's not as funny. All right, so what else? So we got a north and south pole. We talked about repulsion. When are they repulsed?
When the same direction is facing each other.
The same direction is facing each other.
So for example, north and north.
Okay.
When two similar poles fix each other?
Is it when they're not, I just fumbled all the magnetic fields run into each other?
You said next to each other?
Well, because like if it's two norths next to each other, then it'd be pointing at each other.
Yeah, I mean, like repels, opposites attract. I mean, that axiom still holds. There are still magnetic fields here, so if I had a north pole here, I would have two different magnetic field lines right next to each other. They just happen to be going in the same direction. So, how do you create a magnetic field?
Just like how you create an electric field.
There is a difference.
Change the letters.
A little bit more than that. Although there are times. All right. The reason why there's a big difference is that to create an electric field, all I need is a charge. To create a magnetic field, I need a moving charge. So moving charges, or I just say moving, all you need is one. Moving charge creates magnetic field. You could also say that moving charges create a magnet, but typically when we talk magnet, we're talking a macroscopic thing, we're talking something that I can hold in my hand. In that case, you need a whole bunch of them moving. Now, what makes a magnet as opposed to, let's just say, this aluminum right here, is the way that the electrons circle the atom. If I have an atom here, let's say there's my nucleus, and I have an electron that is in essence going around clockwise, or as kids say, the counterclockwise, there is a magnetic field that is created. And the way you know the direction of the magnetic field, our friend, the right hand rule. And again, for you left-handed people, it is not the dominant hand rule, it is the right hand rule. You put your thumb in the direction of the charge, positive charge flow. Again, all this was developed assuming positive charge flow. Put your thumb in the direction of positive charge flow, your fingers curl in the direction of the magnetic field. So if I had a charge, let's make it more specifically, I have a proton that is zipping off to your right. Positive charge going that way, my fingers curl on the top, they are coming out of the board, in front of the board, they're going down, then underneath it's going into the board. So I would represent the magnetic field, and of course, the usual display of flash with different colors. It's coming out and in. You typically don't draw the ones in front because then that just looks cluttered, but magnetic field is going out and in. On the other side of the board, it's going up. All right. So, I'm now about to give you, as soon as I find it, the second physics equation of the course. And the last.
Are you serious?
Yep.
The last one?
The last physics equation.
Is this not the third? Does Ohm's law not?
Does what?
Because we had Coulomb's
Ohm's law was derived from Coulomb's law.
All of that was just Coulomb's law manipulated?
Yep.
Well, give that guy the Nobel Prize.
He was dead by the time they started doing those. And you cannot give Nobel Prizes to dead people. Thus, Rosalind Franklin got screwed.
Well,
I don't have it here, so that is just gonna have to wait. So, that'll be the cliffhanger.
You're telling me you don't know every single physics equation out there?
There are a lot of nuances into it, and I could easily get one wrong, so I think I'm gonna wait. You know, once it gets into my head, it'll be good for a couple months, and then it'll all go away again. Those are Maxwell's equations. Those are all math and definition. Coulomb's law is one of them, and the other one we're about to do is the other one, and then they're all derived from that.
this one.
That is not the one, that actually is sort of derived from the one I was trying to pick up. That is one of the major ones that we will use, but it'll wait.
Is this one?
No.
Biosavar. It's the Biosavar model. Bio spelled B-I-O-T. You probably type in B-I-O-T-S, it will come up. Zavar is spelled like a Zavart.
Let's see, I don't know, that's no way. This one.
That's the one, that's one of the 3 versions of it. Sorry, 4 versions.
Oh, I found the easier version. Oh, never mind, this has calc.
Yeah, it has calc. Anyway, it'll wait.
This is what you said.
I'm gonna bring it up just because it's that attempt to show that it does come from somewhere. I'm not going to, we're not gonna manipulate that in 152. That's a 252 thing, and much to their incredible joy,